Welcome. Now, for the next chapter, let's continue talking about Rolos as an example for real-time distributed operating system. First, I would like to say a few words more. Why Rolos? What is something special in Rolos? Do you remember in the last video, in the last lesson, we saw some reasons why I prefer to use Rolos for these lectures. It's simple, very simple, it's object-oriented, implements building blocks execution platform, and allows software building per composition, and it supports fault tolerance. And it has an integrated middleware for communication, and therefore this is something very special for distribution. If we compare Rolos with other operating systems, we have many targets when we are developing a system. What shall we optimize? Some systems are optimized for speed. They shall be as fast as possible. Others are optimized for size. They shall be very small. Others are optimized for flexibility. They shall be able to be used in every device, in everything. Or cost, it shall be very cheap or something like this. So there are many things where you can optimize your operating system, your target, but for us the most important thing was dependability. Because we are using this in critical devices and we don't want to risk an accident. Therefore, everything which we did, the first target was, is it dependable? And a very important parameter to be dependable and to be reliable is to be simple. So in everything, for every decision we take a look, can be done simple, more simple or not. So do not compromise dependability to get higher speed. So we don't optimize everything. If something is working, it could work faster, but more complex, we don't do that. So we prefer to target dependability even if we lose speed, even if we lose size or flexibility, of course, but we don't want to compromise dependability of the systems. Well, these are only 5 parameters which you can use to optimize your development, what is the most important thing for you, but there are many others. Here, I have a list of everything, of many parameters which could be important for you and which will relevant what to optimize. For example, the configurability, low cost, scalability, availability, security, usability, modularity, generality, or you have time constraints for safety, device drivers, portability, storage, and allocation. So there are so many things which you would like to optimize. Nice, but do not compromise dependability. This was from the beginning the most important point for us and is still the most important point in the development of Rolos. Another thing of Rolos is this is the typical history of not only operating systems, of many applications. At the beginning, they are small. They are to support you. This is, for example, your operating system, and this is you, this is your mission, and this is the most important thing. And this is here only to help you to achieve your mission. So, supporting. Then you go around, and then as time goes, you implement different missions, and for every mission, you get a souvenir. So from every mission, from every application, you get something nice, which you shall take because it was so nice, so you take it in your operating system. So as time goes, the things which you are carrying in your back, in your operating systems, are getting more and more and more, and the overhead is growing and growing and growing. So at time point, it will be maybe bigger than your real application. And maybe at the end it will be something like this, and of course then you had the collapse. So the overhead which you have now is much more bigger than your real application. Actually, it was there to help you to execute your function, but at the end you was concentrating of taking all this overhead, and this was your mission was not anymore the most important thing, but this overhead. And that's the wrong direction. So your mission crashes. And if you see the number of lines of code in your operating system, if the number of lines of code in your operating system are bigger than the number of lines of code of your application, then you have a problem. You are invested more overhead in what support you, what shall support you, than your real mission. So this went in the wrong direction. So we keep to avoid this and keep this as small as possible. So the operating system shall not be the most important thing, shall be not the lines of code drivers, it shall be only to support the mission. And the most important thing is the mission, the functions which you shall implement, and this is the biggest part, shall be the biggest part of the system, and not the operating system. So do you remember, we avoid to reach this point, we try to stay here, like the beginning of every mission. Let's compare with normal operating systems, with normal other missions. For example, the Apollo 11 mission, to go to the moon and come back, really the most difficult action we have done up to now in space applications. It has almost 150,000 lines of code. Then the space shuttle, it was far away, not so complex like the space mission. It went only to orbit and came back, nothing more. And it has 3 times as much lines of code, 400,000 lines of code. And then we compare with small things which, curiosity, Mars rover with 2.5 million lines of code. And the complexity of this was much bigger. And now compare with operating systems. If your smartphone, the Android operating systems, an old version was with 12 million lines of code. If you compare with the Apollo mission, thousands times bigger. What for? To send smilings. Or Windows with 45 million lines of code, Mac OS with 86 lines of code. Use this support in Windows with 100,000 lines of code, and these are all older operating systems. Newer are much bigger. And now let's compare with Rolos. Rolos had 4,000 lines of code and includes everything what we need for space missions. So therefore we try to keep it as simple as possible, easy to understand, easy to explain, and dependable. And why is this the case? Do you remember? We begin here, come here, the overhead keeps growing, and then we have the collapse. Now, why do we have this situation? And this is the history of every software application. At the beginning, you have an original design, you think everything together, and you make a nice design and a nice implementation, and it keeps running. Very nice. But as time goes on, new requirements arrive and you implement new things. When you implement new things, you do not update the design, you just add. And then new requirements for the next application, new implementation, use add, and the design is disappearing. So at the beginning, the most important thing was to fulfill this design, but now you are not fulfilling any design, you are just adding functionality and application. So from every mission, you are adding something more, and at the end, that is what you get. Your original design is not there anymore, it has disappeared. You have a very big fat system without design, and it will not work properly because it has no design. The things are just being added. And that's a very terrible thing. So this is something we shall avoid. But not always it is possible to avoid this. There are sometimes with new functionality which shall be there. In this case, sorry, I say you shall avoid this, but you cannot avoid this. You cannot freeze your system. If you freeze your system, it will die, because living systems keep changing. So as long as your system is living, it will be changing and changing. So do not try to freeze your system. So you are going to have to implement new functionality, new requirements, but we recommend at the same time, when you are implementing new requirements, try to remove the things which you don't need anymore. Maybe when you add these two functionalities, maybe there are some other functionalities which are now obsolete. You shall remove them to have two interfaces to do the same thing. And this is something which we try to do, keeping with Rolos every time when we are adding new functionality, because we see this is something which we require. We see, is there something which we can remove? Because now it's on better, or more general or something like this, and then we keep removing all things. So at the beginning we have a original design, we try to keep the design, at the end we have a final system but with a design and not much more bigger than this. So we keep care to do not grow and grow and grow like I saw before. This is the history of lines of code for Rolos. As you can see, we can keep very stable. So we are adding functionality, but you are removing obsolete things, and we keep stable. And we are trying to remove everything which we don't need, so to reduce the number of lines of code. Another thing very nice, which I said before, is Rodos can be executed on different hardware. For example, PowerPC, ARM processors, Xeon processor, the Intel family, and so on. And it can be executed on the top of Linux or other operating system. We have this hardware-dependent layer. The interface from the hardware-dependent layer to the kernel of Rodos is the same, it shall not change, but this can be implemented for different applications. So we take the kernel of Rodos and we can just move to other hardware implementations, and so we can implement all these applications in many different types of CPUs on many different types of computers without having to change anything in the application. The only interface to the application is the kernel. Everything else is done transparently for the application. So we can move from CPU to CPU and the applications will stay the same. Well, this is something which you can find in many operating systems. That is something quite normal. But something special, this hardware-dependent layer can be implemented on the top of other operating systems. So we can run on the top of Linux, of Windows, of Mac OS, on POSIX, and many others. So for the implementation, for the development, we can use other operating system, your desktop operating system in your laptop, and you don't need the target hardware. By the way, something very important, Rolos is open source. If you like it, you can take it from GitLab. Okay. Another thing which I mentioned is it's a framework. And this framework consists of passive and active objects. The passive objects, they are passive. They provide some interfaces, and another object has to call these interfaces to execute some services. The active objects, they are called by the underlying system. They have interfaces which will be called by the operating system, for example, to react to an interrupt or time events, or just to get the CPU time. So they are the ones who have the control. The operating system will activate these objects, and these objects will use the passive objects to implement services. So this is the difference between the passive and the active objects. The active objects are activated by the operating system, and the passive objects are activated by your own active objects. And then we have different layers. We have the core, and the core supports the local resources of the CPU. Of the computer. For example, CPU, memory, input-output devices, or something, and all this. This is the local resource management, what is normally the function of an operating system. On the top of this, we have a middleware. And the middleware is for communication. So we said before, we want to implement as building blocks. So different applications can be plugged on the top of this operating system. They shall communicate with each other, and then we implement very complex functions by composability, just adding functionality. And this is the function of the middleware, the communication between applications, but this is limited to the same computer. If we have applications running on different computers, then these applications shall communicate with each other. For this, we have the gateway. And the gateway, here's the local communication in the computer node, has access to some hardware links. For example, we have a CAN bus, a normal UART, an RS486, E2C, SPI, Ethernet, or other kind of protocols, SpaceWire, or any other kind, and then it transforms these communications, software communication calls, to this hardware links, and then it sends the data through the network. On the other side, another gateway will get this data from the network and distribute locally. See, the gateway is what we need to interconnect different computers, something like this. If we think in hardware, something like this, we have different computers, we have the network, and the interface to this network is the gateway. So we can have many applications and they can communicate with applications in the same computer or in the same node, or with applications running in other computers in other nodes. And this is done by the gateway. And this is transparent. So when two applications are communicating, sending data and getting data, you don't have to take a difference. Is the other application running in the same computer like me, or it's running in other computer? You just distribute your data and the gateway will bring to the place where it shall be executed or gotten. Okay, and now let's talk about the core, the administration of the local devices. In Rolos, everything is controlled by time. I would like to say something. It could look like I am talking only about Rolos, but this is true for many operating systems. So I am talking now generally about operating systems, and I am using Rolos just as an example. So it's not very special what I am saying now. This can be used by almost every real-time operating system. Okay, I said before, a Rolos is a real-time operating system, and therefore it's controlled by time. Almost all applications, all events inside of the Rolos will be triggered by time points. So you say when we shall substitute or preemption to switch from task to other task, when an application shall be started to perform a function or something like this, and all this is controlled by time. So the function of Rolos is every application will give you sometimes the operating system and will say at what time shall be executed some action. And the function of the operating system or on Rolos is to take these time constraints and try to execute everything so that these time constraints will be satisfied. In case there is something wrong, development or the programmer made something wrong, and it is not possible to satisfy all these time constraints, then we use priorities. So there is something wrong. We know it's not possible to satisfy all these time constraints, so we have to take the decision what is more important, and this will be executed first. These time constraints will be reached, and the other, which are not so important, will not be reached. This is the best thing we can do, because the programmers make a mistake. He was requesting time constraints which are not feasible. So we are trying our best, and for this we use priorities. Okay, and then we have exclusive regions. That is some kind of synchronization. For example, input-output devices, we shall avoid that different applications access some devices at the same time, because it can produce a chaos. If you get some data from one application, you are not concluded, and then you get some data from another application to the same device, then it will be a chaotic situation. Therefore, we have to protect devices. A task might say, okay, I'm going to use this device, no one else. And then this device will be blocked. This is exclusive regions. Until the application concludes and says, I am done, then the next application might take this device and continue working with this device. And this is the function of exclusive functions. Protect some resources, and for this we use something like semaphores. I'm going to explain semaphores later. Okay, and now how does it work with Rolos, the Rolos core? Do you remember we control everything using time? It's a real-time operating system, and it is a preemptive operating system. So if a task doesn't give cooperatively the time, and it has been using the CPU for a long time, then Rolos will interrupt this task and the next will continue working. So the time management is a central point in the application, in the implementation of this operating system. And the time is managed as an ongoing time. It begins as 0 0 is the time when we boot the system, and the time continues incrementing and incrementing until what we call end of time. And this end of time is the overflow or of time counter. Our time counter is a 64-bit counter which counts nanoseconds, so a very fine time resolution. And if you count how much is 64 bits counted in nanoseconds, then will you see it's about 150 years in the future. So the time limit of every Rolos system is 150 years. After 150 years of continuous operations, it will crash. But we can assume nothing what we are building now will run continuously for 150 years. Therefore, it's not a problem. End of time is very far away. So, and it works like this. That is a timeline. It begins at 0. This is the time now. And this time now is moving to the future, going to end of time. And everything very important. Many operating systems use relative time. So a loop begins at 0, concludes at some time point, and then it comes back to 0. We have found this makes a lot of problems and can cause a lot of mistakes. So we don't have cyclic times. We have only these linear times who never goes back. And all time points which we specify, they are absolute time points. We don't say something like activate in 3 seconds or activate in 5 seconds. We say activate at 12, activate at 12 and 3, activate at 12 at 4 seconds or something like this. But never relative to any time point, because it produces a lot of mistakes, because this relative point is moving. And then it's very difficult to know what did you mean with in 3 seconds, because in 3 seconds relative to now, and this now here is moving. So we avoid, there is no way in Rolos to implement these relative time points. We work everything with absolute time points. Okay. We have this already, and I can show some examples how it works. Let's see the Rolos thread. This is something like an application. We have many threads which can be executed at the same time when, say, many tasks or many applications which are being working continuously. Let's see how it works. There is, in Rolos, when you are implementing a Rolos program, you don't have something like a main, but you have threads. You can have many of these threads, and every one will be activated as soon as it's possible. So you create a class with thread, and this thread has the different things which you need. Each thread has its own stack. It has a stack pointer and a context. So when we switch from thread to thread, or from application or from task to task, there is some context which shall not be lost. Then the operating system take a snapshot of the state of the registers of the CPU and writes in this context. So this task can be suspended. Nothing was lost, and the next time the task will be reactivated again, we list this context variable and write all CPU register and everything which is important, so the task will not notice it was suspended and someone else was working, because we are restoring everything as it was before it was suspended. And this is this context variable. And the stack is what I showed before for your function calls. Then we have for every task a priority. So normally you don't need priorities, because everything will be executed at some time point. And if the task was well designed, then we will have no time collisions. This will be executed, and when this is concluded, the next thing will be executed. But if the programmer makes a mistake and you have time collisions, two things shall be executed at the same time. So these time constraints cannot be fulfilled. What shall we do? We shall take the decision what is more important. And therefore, every task has a priority, and then we can say, okay, something cannot be done. We have the time collision. Let's select the most important thing, and this will be executed. And all other things else shall wait. The best thing we can do. And I said before, we have everything is controlled by time. For every application, we say when this application shall be executed and when it shall be stopped. And this is just a variable. This variable says suspend until. And this says when this task shall be activated. So we just write in this time, 64-bit, when it shall be activated, and then we know as long as this time point is in the future, this task will be not activated. The time is moving, the time now is moving, and when now is as big as this, then this time, this task will be activated. And if we want to suspend, for example, not for a time point, for waiting for input output, then we write here in suspended until end of time. And this task will be not activated by time. When the event arrives, which we are waiting for, then we set here in this suspend until 0, and then this task can be activated already. So instead of this complex state machine to control the state of the task, we have only one variable. And this variable controls shall be executed, shall not be executed, is waiting, or is ready to be executed. Okay, and then we have this interface when we say when this task shall be activated and when it shall be suspended. Okay, and so it works. We have a macro view and a micro view. From the macro view, all tasks which are ready will be executed at the same time from the macro view. Actually, we have time slots, but if you take a macro view, you have the impression all then are being executed at the same time. So let's assume we have these 4 threads, tasks, applications. Okay, and they are being executed all concurrently at the same time. The time is going here until they say suspend. I don't want to work anymore. Let's suspend until the next second. So, for example, this thread could be executed once per second. It runs for half second, then it waits again until the second, and so on and so on. Then this is a suspend caller until, so it will be suspended until the next time point. This is 1 second later. And then it will be executed until it makes suspend, and then 1 second later, and so on. Or it might be not periodic. It can say, okay, I'm going to be suspended until this time point. At 12, I have to do something at 12. Then I suspend myself, and at 12 it will be reactivated until I make suspend. Or then will be working until here, and then it has concluded. It doesn't need the CPU, never again. Then it makes suspend me until end of time. Then 150 years in the future will be reactivated, but it's, for us, not important. Or it can be suspended and say, I am waiting for an event. For example, data from this device. When data from this device arrive, activate me. And those are the events. This event will be activated, for example, a hardware interrupt, and it knows, okay, the processing of this event will be executed by thread A. Then I make a resume, and this thread A will be activated, and it will continue working. Okay, and I can generate time events too. So I have threads and I have events which will be activated by hardware interrupts. I said before, this is a macro view. We have the impression all of them are going to be executed at the same time. And we saw before, it's not possible. We have only one CPU, and then even if they are being executed at the same time, we have to create time slots. And now let's see only a very small part of the time, this. And let's amplify this time, and let's see how it's the reality. This is the micro view. Okay. In this micro view, this very small part, we have time slots. Not 2 threads can be executed at the same time. So this will be executed until this time, and then it makes a suspend. And then it will be, it's the one with the highest priority, so it will get the CPU until it says, I don't need it anymore. Okay. And then this will be activated. It will be executed when this is concluded. It has a lower priority, so it cannot interrupt this until it makes a suspend. And then there is one with the lowest priority. That is priority 0, and is doing something which is not important, just consuming the rest of the time. But at this time, it didn't make a suspend, but this thread was reactivated. Maybe it says suspend me until this time point. and then it will be activated, and then we have what we call the preemption. This doesn't want to make a suspend, doesn't need to make a suspend. The operating system will, per preemption, suspend it, and then this thread with higher priority will be activated. It will get the CPU. Maybe we get an interrupt, hardware interrupt. This is an event. And this has higher priority than all other threads. This in hardware events. Then this will be preemptive. We call this interrupt service routine. We execute the interrupt server. The interrupt server will continue, and then we continue with the execution of this application. So if you see the micro view, only one thread has CPU access at any time point. If you look the macro view, you get the impression many are working at the same time. Okay, and now how it works, the typical state machine. Do you remember from the last lesson, we saw this typical thread state diagram. At the beginning, a thread will be waiting, then it will be ready to be executed. From the ready, when it can get the CPU time, will be running, will be executing, and then there are different options which can occur here. It can be per preemption be suspended and will be moved to ready, and another will get the CPU to be executed. Or it can wait for a signal from a device, then it will be moved to waiting until this device delivers the data, and then it will go from waiting to ready to be executed. Or it can say, I want to be suspended for 3 seconds. Then it will be in this suspended mode until the 3 seconds arrive, and then it will be ready again. And then as long as no time constraints or no devices are accessed, we stay in this loop. It will be running, it will be interrupted to execute another, the other will be interrupted, we take this and will be executed again. And this is the typical thread state diagram which we find in many operating systems. In Rolos, we don't have something like this. We have only a time variable, and that is the time now and suspended until. And do you remember, time begins at 0 and continue growing and growing and growing until end of time, 150 years in the future. This time point is what we call now. This is the future, and this is the past. And for every task, we have only this variable which says suspended until. If suspended until is bigger than now, then it will be not be executed. It's in red, waiting until something will be, until the time arrives. All which are in the past are ready to be executed. So it was ready to be executed here. It has been long ready to be executed, and this is the one which is running. As you can see, in a perfect design, you shall have only one thread which shall be waiting for the CPU at any time point. But here something went wrong. The designer was not taking care, and you have many time collisions. So all these threads want to be executed now. But in this case, we select the one with the highest priority. And let's say this is the one with the highest priority, and this will get the CPU. Until it says, okay, I am ready, I can be suspended, and it will go to the future, and then the next one will be activated. Or the time is moving, let's say the time now comes at this position, and this one has a higher priority than this, then per preemption, this will be interrupted, and this will get the CPU and continue working. And so, task will be activated as soon as this now reach this time point of suspended until. Do you remember this suspended until? Let's see the internal state of the function. This is this suspended until. And this is which says ready to be executed, or it shall be waiting for something in the future. Okay, and that is something very simple, a very simple implementation of the time scheduling. And if some application is waiting for something which is not time bound, then we say suspend until end of time. And it will be here, for example, until data arrive. And if data arrive for this thread, then we set it suspended until to 0. And then 0 is always ready to be executed. And if it has the highest priority from all other which are ready to be executed, it will get the CPU and will be executed. Okay, the next thing is the communication over the middleware. Up to now, let's go a few things back. We were talking about the core, the local resources management, memory and CPU time. The next point is the middleware, communication. Here, the communication between applications. Okay, normal communication in the same processor uses shared memory. Okay, if several tasks shall be working together, a very simple way is they get a shared memory and they have some variables which can be read and written by two applications or end application. But this is very dangerous. You have to be very carefully who is writing what and who is reading what, and you know to know the position of every variable which shall be shared by different applications. So this is a very primitive, a very simple way of communication, of working together using shared memory, but very dangerous. I do not recommend to use this. A more elaborated way is to use messages and message queue. So we have task 1. The task 1 will produce some data which shall be required by task 2. Then it prepares everything in a message and writes in a FIFO, a queue. Later, this task 2 will be activated. It takes a look to this FIFO, to this queue, gets the data, the messages which it needs to be processed, does something, and if it has to send data to other process, to other task, it writes in another queue. So it prepares a format, a message, and sends the message to the corresponding queue, to the corresponding task. So it's a little bit more overhead than here. Here you have to prepare everything in messages and write in FIFOs or queues, and the other one has to get this message and interpret. It's more overhead, higher complexity, but much more safe than this. This is very simple, but very dangerous. You can make a lot of errors there. Well, how we do it in Rolos, we have something similar. We have threads or applications which are doing something. We have a middleware to send and receive messages, but this is the next step. The first step to communicate is in asynchronous buffer and asynchronous FIFOs. So you can write any type of data, if you like single words or some kind of arrays, and this FIFO can be written for this thread and read from this other thread. Something very similar like this. But it doesn't need to be a FIFO. Sometimes you need only a data, and you need the current data. For example, you need the temperature now. So you don't need the whole history of all temperature measurement. You read only what is the temperature now, and therefore we have this asynchronous buffer. It has an internal, very clever structure to avoid inconsistencies. So every time you get data from here, you will get a consistent set of data. The last totally complete written set of data. If it is only one word, then there is no problem. The writing and reading a word is an atomic operation. But if it is 2-3 words, maybe be aware. Maybe you are writing the first word, you are ready to write the second word, and then an interruption occurs, and the other application will get the data. It gets the new first word, and the second word is not written now. Maybe it will get all data, and then you get an inconsistent messages. So therefore, we have here a buffer where the writer generates all the messages ready, and then only one pointer will be switched. And then it gets a consistent, complete message, but only one, the last one which is written. And if it reads n times, it will get n times the last message. So it will get only the current state or the current measurement. So you don't need to use a buffer, you need only the newest value. And this is what we do in this asynchronous buffer. The next step is the middleware. This is a very simple, very primitive. It's something like shared memory, but well-organized shared memory. The next thing is using messages in the middleware. So you have different applications, and they may be running in different computers, in different nodes. From the top, we have the layers. On the bottom, we have the hardware and the CPU. Then we have the hardware-dependent layer, and then we have the kernel of the operating system, in this case Rolos, and then we have the middleware. And the middleware takes messages from any application and forwards to any other application, even if they are running in different nodes. So to cross this barrier here, we have the gateway. But this will come later. Okay, first, as long as we are in the same node, we don't need this gateway. And this middleware might distribute the data from any task to any task using pointers in shared memory. But it doesn't look like shared memory. It looks like forwarding messages. Okay, and so is how it works. What we have implemented is a publisher-subscriber protocol. And for these publisher-subscriber protocols, we can have many communications channels. We call every communication channel a topic. And for every topic, we can have many applications who publish data in this topic, and we can have many applications who subscribe data in this topic. First, let me see, we can compare it with newspaper. When you write something in the newspaper, you don't know who is going to be the reader. You write only, you publish it in the newspaper. And every newspaper might have many opponents. So many different persons may request this newspaper, and everyone is going to get a copy of this newspaper and is going to get this data. So the publisher, the one who is writing the newspaper, doesn't know who is going to get the data. And this is the publisher and the subscriber. And we can compare this with the topic. So every newspaper here will be a topic. So you are writing to a newspaper, you are writing to a topic, and someone else is going to get a copy as soon as you are ready with this. Example of topics will be, for example, the speed of your system, the temperature of your system, the position, the voltage, who knows what, any data which you want to publish. So let's assume this one is computing the speed. It makes some internal computations and it has the speed ready, and then it makes publish the speed ready, and then it can continue working with something different. Then the middleware shall know who needs the speed, who are the abonnents or who has subscribed the speed. And then we can see to this topic, we can see this one can write, this where can read, this reads, this only two. Only these two devices are reading the speed. So every time he publishes the speed, he doesn't care. The middleware will see he needs the speed, then he will get a copy of this message, and he will get a copy of this message. So only one subscriber, and maybe 0, 1, 2, 3, and one publisher, and maybe several subscribers. We don't know how many. And something more, maybe more than one application is publishing the speed. So we don't need only one publisher. Anyone who has this speed might publish this, and these are going to get data for this. Something similar like the temperature, let's see. This device is publishing the temperature, and no one gets. Who cares? He is just publishing, and no one gets this data. Or the position, this device is publishing the position, and who knows this, and this device is getting the position. And how it works, this publisher-subscriber protocol for this middleware. Okay. And something special, all communication in their system are based on the publisher-subscriber protocol. And it makes no difference who is the publisher and who is the subscriber. And we can mix between software, devices, and hardware. So even hardware devices can publish data, and software applications will get this data. Or software applications may publish data, other software applications might get the data, or even devices or hardware devices might get a copy of this data. So that is very nice, transparent, so you don't need to make a difference, software, hardware, software, or any combination of them. Okay, A publisher make the messages public on a given topic. Subscriber, 0 or more, will get a copy of this topic as soon as they are published. And for this communication, it makes no difference in which node the publisher and the subscriber is. You use publish, and the subscriber in the same node or other nodes will get a copy of your data, or even hardware devices. And to establish a transfer path from publisher to subscriber, you don't need a complex protocol. The only thing you need is a common topic. And the common topic is identified just by an identifier and a data type. And that's all what you need for the communication. Okay, for now, let's conclude this chapter here. Thank you very much.